Or
I personally, yeah, we'll go respond this at all because it's the
I was just
program.
though. I'm gonna lose the game.
I don't know if I did pretty good on my theory.
Way too much for me.
Yeah, 159.
Okay, now that you're early, I can
161. Yeah, with that 5 on my own. So I really was okay.
Oh yeah, you are even done with your.
Did you not have a class for this day?
Yeah, normally I had a test, so I finished early and I was able to get here for like 1 hour.
Yeah, that's I'm really like another class I have immediately after this the one that if we go to like memorizing stuff. It's all online anyway, it's all recorded. I don't really know. And besides, it's not very hard class, it's entirely project based.
What is it?
330 systems.
Start with.
Yeah, I guess you're operating system.
Actually, this particular thing does not have operating systems and analytics and stuff. It's like memory management, process management. But it's not very.
Couldn't do it. My game was too bad.
Our reason was fun as well.
Honestly, I'm not like super stressed out.
Oh, it's an interesting. Did you see the resources like I put in the Discord server?
I did.
Like I was also.
The book actually covers this stuff as well. It's super interesting. And it goes.
Right there.
This I think doesn't give a lot of examples, but that is
Yeah.
more diverse information. I think.
All my times today, it's easier than make 343.
I do a lot of Georgia Tech had a good slide deck.
It is what it is. Though. At least I'm well versed in terms of linear transformation.
Like 445 or something.
You have to take 371 for that.
You have to take 300 for that, but I haven't taken 300 because I didn't know you could take 300, but I'm gonna get an override if I can.
Yeah.
Like I don't.
The one was the one that came to me first.
Yeah, I don't really know how important.
No,
No, that's why I don't.
Yeah, like I was talking to people taking both these they're basically the same class. And let them name all their Christian classes. I have a couple of Christian problems in that area that I'm obsessed with, so I really want to take class.
This comes back really negative. You weren't getting stronger.
Yeah, I mean, you're taking classes that are you also taking you're also taking a bunch of classes that aren't really necessary for CS.
Yeah, but
It is.
I don't understand. I didn't think I got a single thing out of 343s.
No, 343 was like just review for me. I do material.
I see. Yeah, but overused everything you saw in that class.
Because they'll
Solved every question.
Yes, exactly. You might like see if you can. If you're like, it's not very hard, but like some of the questions. Just take it. It's gonna be miserable while you're doing it, but like it's best to get it over with. So you can get all the interesting stuff.
Okay, so like
That's normally people recommend not taking the first, but like I mean
I also have to say about like upper division. HU, SB, stakes. Also, what?
always me.
Are you using like word?
Some people don't spy on me.
Why?
Some people don't look at it. They just live blind.
Why? Just what kind of man is it?
It's anti-surveillance.
You took the effort to get off of the.
It started. I think it was just online.
I can't believe.
They gave me 100 back, so it was like, kill the transfer. The channel, kill the transfer. How did my name? How did I fail the transfer? Until it took from me. What? That's dangerous, actually.
I'm allowed to go back and down.
The time they use it.
I'm not. Whatever.
That's like pre-math learning, right? Pre-math way of learning.
It's been the first time I've ever seen your face on this board.
It
was at a point where I just. It was like, okay. I recognize that they're just small experience.
Okay. Yes, so there's been an email sent regarding the exam situation. So it will be next week end mostly. So we'll have a take home that you will do over the weekend approximately, and then submit it online. Yeah. Before that, we will have the exams. So the two homeworks and the graded homeworks as well as the solutions will be provided to you. In terms of questions, the way the take home will work is you can ask a lot of questions beforehand. General, can you explain how it works questions before the take home is given? But I will not answer, or we will not answer. Can you explain again how this particular thing works after the take home is given? You understand what I'm saying? Because you are supposed to have figured out. So that's to stop you from waiting until the take home comes and then just say, can you tell me how to do these problems? Which is not actually take home, it is begging, more like thing. So you can still ask clarification questions. You can ask questions that if you're not sure whether it's clarification or whether it is something else, you can always ask, and then we will decide. And we will certainly not give repetition of how to do something, but you can always go and look at the notes in class notes and everything. Yes.
I'm confused about the time frame. So it's over the weekend for the time frame for the exam. Did we get on Thursday or is it Friday, Saturday, Sunday?
I'll have to figure that out. Yeah. Other questions? Yeah.
Are we allowed to use the notes that are there on Berkeley's website?
What?
Are we allowed to use the notes that are there on Berkeley's website?
I prefer that you only use things that you learned in this class. Okay, that's my general thing. But if on the other hand, you spend time reading other stuff and took notes yourself, it's fine with me. It is what I'm saying. I can't change what's in your head. So I'm not exactly against trying to figure out how something works after seeing the question, but at the same time, there is like a thin line between trawling for the answers.
Not calling like
I mean, again, what I'm saying is I can't tell, right? That's why I think it's the basic idea would be that you can take any of the things that was here as well as the textbook, Okay. Other questions? Okay. Yeah, so when I started when I was getting ready to do machine learning, I thought I'll get a t-shirt so that I'll wear my machine learning t-shirt. Do you guys see that? That's the definition of an algorithm. I don't know if you can see that. It says an algorithm is when programmers don't want to explain what they did. A heuristic is when programmers can't explain what they did. And a machine learning is when programmers don't know what they did, right? Which is as good as it gets in terms of understanding the concept. So I saw this t-shirt, I ordered it, and then they took their own sweet time making it, and then they only sent it to me in the beginning of this week. So since I don't have an Instagram, and since anyway the machine learning already started, so I put it on my Twitter, and it has, by AI standards, gone viral. So much so that people are separately making this t-shirt. So, there's a viral t-shirt company which just takes any t-shirt that's become viral and they start making it. So, they're not buying it from where I bought it, so they're making it themselves. So it's kind of sad that I am wasting my time trying to teach on Twitter when I could have been a t-shirt model, apparently. And I get a lot more, I guess, impact that way. But anyway, so that's that. So what we did last class is we were looking at perceptron units, and then actually let me just do the following thing, just give you a sense of where we are going before going. So we'll review the multi-layer neural networks today, which is what we already started doing that last time. Then sort of say that backpropagation can be done in multi-layer neural networks too, but and then you don't have to do it every time by specifically computing the partial derivatives and the gradient using chain rule. You can just sort of automate the gradient computation in one fell swoop. And once you figure that out, then essentially you can assume that this is solved. So pretty much any arbitrary function, which is a composition of other functions, like for example, sine x squared would be starting from x, squaring it, passing it through sine. That would be the function, right? Anything you can think of will be a composition of functions, where you can have elementary functions as well as the usual operators like plus, multiplication, max, etc. So you can basically say that in the end, you will be trying to differentiate some arbitrarily large function, which is a composition of many functions. It's very painful for you to actually apply the chain rule by hand. There's not enough paper in the world to write down the gradient, but you can basically just do this recursively. Is a forward pass and a backward pass. You see what I'm saying? So, and we will get that sort of understood. I mean, I sent a link to you guys. I hope some of you had a chance to look at it. If not, definitely look at it after the class. You need to have sort of the metaphysical belief that this can be done without problems, because then everything else can just be saying, I can reduce it to an already solved problem. Do you understand what I'm saying? One of what happens today is after we figure that out, that backpropagation basically helps us in computing the gradients, and gradient descent only needs gradients to actually decide how to make a small move, in the opposite direction from the gradient, right? Once you know that, then one of the strange things we will start doing is we will basically, because we'll think of gradient descent as this, I like to call it a very slow, rich uncle. Okay, because gradient descent makes small changes to the weights. And if you do them often enough, asymptotically, you will fall into some sort of a local minimum. That would be some sort of a minimization of the function. And we realize that machine learning essentially involves sort of minimizing some loss function, right? So we will basically, one of the things we'll do is, since we know that this rich uncle has been automated in this backpropagation come many epochs of gradient descent, Okay. We will just basically start saying, well, we can write any arbitrarily complex loss functions because somebody will take care of it. Okay. And also in the middle of the neural network, we will start introducing arbitrary parameters that need to be learned. In fact, we will talk about this very interesting idea called batch normalization, which is a mind-blowing idea where you're trying to normalize the activations at each layer. I'll come back to it again, but normalize it such that they'll have a certain mean and a certain variance. The right kind of mean and the right kind of variance. What is the right kind of mean and the right kind of variance? Well, let the slow rich uncle figure that out. Do you see what I'm saying? So the slow rich uncle is anyway figuring out what are the right weights by slowly changing the weights. Uncle, I guess, so he will figure out how to change also these arbitrary parameters that you're throwing in. You see what I'm saying? So this part you need to know for sure this can be done because everything else essentially just gets reduced to this. Okay. And then so we will basically talk about, after that we'll talk about these some simple engineering tricks in terms of making sure that networks actually converge faster and don't get into one of the problems that they have, which is zero gradients. If you have zero gradients, then essentially the weights don't change fast enough, and so basically you can do lots and lots and lots and lots of iterations and nothing will be changed. Okay, and then so we'll look at some of the ideas there. And then in fact, the biggest change, which hopefully we'll start today and then get into more the next class. And in between, I will actually make you watch a video from last year too, is there's a bunch of techniques. Basically, you can think of improving the generalization. Remember this distinction I made between learning and compression and generalization? Much of what we're doing up until now is just compression because we're just trying to minimize the loss function. Loss function is defined in terms of minimizing the error. So the question then is, how do you make sure that the generalization improves? And to some extent, these ideas, regularization and Bayesian learning, are general ideas for machine learning. We're just going to look at their versions in the context of neural networks. Okay, and then finally, one other way you can improve generalization, it turns out, is using specialized architectures. And so upfront, we will assume that the multi-layer neural networks, if nobody tells us anything, they are fully connected networks. That means if there are, let's say, I1 to IN, units in the initial state, and then the next layer has M units. So let's say this is N units of initial state, initial inputs, and N units in the initial input, M units in the next level, and K units in the next level, and so on. So then you will assume every unit is connected to every other unit with some weight. You see what I mean? That's called fully connected or dense networks. If you don't know anything else, that's what you will wind up assuming, that's what you're doing. Okay. So that basically, instead of that, we will look at specialized architectures which sort of reduce the number of weights you wind up having to learn. Okay, so one thing to have in mind is, in some sense, fully connected dense networks will learn everything, but they learn it slowly and they might also not generalize well. Whereas these specialized architectures might sometimes wind up letting you learn much fewer weights. And one example of that we will look at is convolutional networks. And in general, you can also think of it, even though we'll talk about convolutional networks because you all want to know about it because it's used in images and all that. But really, in fact, I might get into it today, but also you might see it on that lecture that you'll be watching over the weekend. You don't need to do connet kind of an idea only in two-dimensional images. It can be done in any kind of a data. All you are essentially saying is, if you have, let's say, N initial states, initial units and m next layer units. Before you are connecting every unit here, I'm sorry, connecting every unit here to every unit in the next layer. And then you have to learn all those weights separately. So there are n times m separate weights. Imagine some strange thing. I'll say, no, I'm going to only I'm only going to buy 100 weights. And I'll just keep shifting those 100 weights along the nodes. You see what I'm saying? Imagine there's like some kind of a brush sort of weights, and this brush is being moved up. If you do that, it's a strange kind of a network where what is happening is, even though there are still n times m weights, many of them are the same value. It's only basically going to be 100 different values. So you will wind up having more examples to learn each weight. One of the biggest problems you will find in learning in general and neural networks in particular is oftentimes you'll wind up having more weights than there are examples. Okay, that means you're going to have, let's say, 100 examples and you need to learn 1,000 parameters. Makes not too much sense, right? And in fact, if you have too many weights, one of the biggest issues that we'll also talk about theoretically is, if you have 1,000 weights, you can do almost zero loss compression by just using weights to remember the examples instead of learning any structure of the examples. You see what I'm saying? So in general, we'll reduce the number of weights by sort of doing weight sharing. And one great example of weight sharing is concatenates. But there are other ideas. And concatenates are useful because they're used in the images. In fact, one-dimensional concatenates is kind of idea that I was talking about when you take the brush up the weights, both sides. Any questions on this? This is where we are going. Questions? Okay. So we basically looked at these multi-layer networks, and we basically agreed that they are a way of essentially allowing for learning more complex functions than the linear functions. Okay, and in particular, we talked about these theoretical results that any continuous function can be approximated to any degree of accuracy by basically just one hidden layer, a neural network with just one hidden layer. It can be arbitrarily wide, but it only be one, it's basically two layers. That means one hidden layer. Okay, there's an input layer, there's an output layer, and that if you just have input layer and output layer, that's called a perceptron. And if you have an extra hidden layer, then essentially that's a hidden layer, that's a middle one. Okay, it's enough if you just have one hidden layer to get any continuous function, and it's enough if you have two hidden layers, you'll get any discontinuous function also. There is theoretical results on that. And we kind of try to understand why that is true from the perspective of the kernel machine comparison last class. That if you took the initial features and took arbitrary functions of them, and so you basically started from an n-array input and you made it, let's say a 10-dimensional input, and you made it into a million-dimensional input by essentially arbitrarily defining new inputs in terms of the original inputs. So if you have x1 to x10, I can make extra inputs like x1 square, x1 cube, x1 power 4, x1 power 5, etc., and x1 power 5, y1 power, x2 power 7, etc. That's one more feature. So you can make infinitely more extra features. And there are theorems essentially. Again, how many of you have taken time to look at the Quanta article, the Quanta magazine article? Okay, the people who wind up raising their hands, those are the ones who are getting things out of this course. The rest will probably pass the course, but the difference between passing this course and getting everything that I'm hoping you will get is vast. Do you understand what I'm saying? Most of you will pass the course. We'll make exams easy enough that you'll pass. But I'm hoping that you will get a lot more than passing the course. So if you look at, for example, that Quanta magazine article, that was just published this week, right? And it sort of tells you, and it's basically trying to tell people what's happening in theoretical machine learning. And essentially, the best we know is kernel machines and neural networks are connected. Okay, so you're kind of at the bleeding edge of understanding, even though you're supposedly in the introductory AI course. This does not happen in physics classes. Unless you take physics 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you won't get to the bleeding edge. In AI, you can easily get to the bleeding edge if you want. Okay, so that was the multi-layer stuff. And then we looked at the fact that I will not go into this. So one of the things, of course, is can we still do the same sort of gradient descent with respect to the multi-layer neural networks? I mean, and the point is that it can be. And so I will first show you that you can do it in first principles way. It's sort of fx plus h minus fx by h way. And then say, who the heck cares about that? We will just automate it using backpropagation, for which you need to understand the backpropagation algorithm. Okay, and both of them, it will be useful to understand. And one of the funny things actually is historically, this stuff, again, this is one of the other interesting things about science. I mean, basically people can decide something isn't working for all sorts of reasons. And there are a variety of reasons why people for the longest time assumed that multi-layer networks cannot be trained using chain rule, which is what we looked at before. And in fact, a strange thing that happened was for the perceptrons, the way the weight change rule was being invented, it was being invented in terms of errors and the inputs. Okay, and that sort of a intuitive way of thinking fails when there is a middle layer, because you know that the inputs are one layer behind you, and so you don't quite know how the error in the output is being caused by the inputs, which are one layer, separated. So credit blame assignment becomes hard. So there's a lot that was written back before 1980s about, oh, we really have this problem of credit blame assignment. Instead of just saying, if you do the chain rule, that will take care of it. It's easy to say right now that how can people be bozos, but all our ancestors were bozos. But they were sufficiently non-bozo enough that you're still alive. Those people whose ancestors were even more bozos than your ancestors, they don't exist, because they probably got run over by buses. You see what I'm saying? Okay, so we were thinking all sorts of random things. So one of the random things we thought, like 20, 30 years back, is you need a whole entirely new theory about how to do multi-layer neural network optimization. Now we say it's the same thing. And in fact, you can spend time reading this. This idea has been rediscovered multiple times. And one of the other complicating things is, even if you're doing gradient descent correctly, you may not actually find the minimum in your lifetime if you have cheap computers and very little data. You see what I'm saying? Which is exactly what we had, cheap computers and very little data. So when something isn't working, you could either say, the idea is right, I just need to wait for the world to catch up with it, or start doubting yourself, saying maybe there's a new theory of how to optimize these functions. People tried both. People, including Hinton, were trying both. In fact, I keep saying that Jeff Hinton, if you go to his webpage, he still has a neural networks course that he gave in 2030, okay, on Coursera. It's a very nicely done course. And it's like basically getting it from the horse's mouth, because he's done a lot of this work. And you notice that most of what he was saying was, look, we know that multi-layer neural networks cannot be trained. We need to find other fancier ways of somehow speeding it up. And it turned out all the brain was not needed because the computing became cheap. Do you understand what I'm saying? And so in a weird sense, it's like an anticlimactic thing. There's all these beautiful algorithms he talks about how to train, like sleep-wake algorithm, this, that, etc. You don't need any of this. In fact, you can just do backprop. In fact, you don't even need to do backprop. You call, you set up your architecture and PyTorch will do the stuff. And it's easy to say that, oh, that's obvious, but It wasn't obvious even to the people who are at the very edge of doing it. Again, because nothing was working. And when it isn't working, is it because the tools are bad or the craftsman is bad? And we've always been told that only a bad craftsman blames the tools. Right? Anyway, so keep that in mind. So everything else that you're doing is because you are alive at the right time. So you don't have to, you can avoid all the mistakes other people did. So all you need to do is, so if you have multiple networks, then basically you just need more notation. So imagine this is activations. We'll call the activation of a unit, which is basically the G of its weighted sum of inputs. So we'll call that, this is activation AI, this is activation AJ, this is the input units, we just call them activation AK, but they really can be also called IK. And then there are WKJs, which are connecting these units to these units, and WJIs, which are connecting these units to these units. If you just had a thing of this size, or basically more like if you have a network like this, then that was just a perceptron. You know how to do it. So the problem is there's more layers, okay? And people just got stuck there, essentially, okay? In fact, there are all sorts of funny stories in that thing that I don't want to go into, including how Hinton rediscovered, this idea has been discovered multiple times, and he rediscovered this in 80s again, that in fact we should depend on the backpropagation, and then he got it published in Nature, and that makes a difference, it turns out, so people started paying attention. Anyway, so the way you will do it is to do exact the same thing that we did last time around for perceptrons. If you want to derive the weight update rules by yourself, by hand, okay? Nobody any longer derives weight update rules, okay? But we should know how to do it once, okay? So you basically still take the weighted sum, weighted error difference, yi minus ai square. And by the way, this is still online, not batch. Not batch, because essentially what we are thinking is this network may well have multiple AI units. So it's like it's like multi-class perceptron, okay? So it's still looking at minimizing error with respect to each example in this computation, okay? So I'll wind up taking the error. I'm not going to walk you through all of it. I'm just saying that it's there, that I can look at the error here, and then I take the partial derivative of the error with respect to Ji, and that will get you, after simplification, some minus aj times gradient I, where essentially what we are saying is the amount, the weights here have to change depends on the gradient and the inputs from here onwards. And input from here onwards is AJs. Okay. And similarly, the next level will be more painful, but it's actually, there's going to be an extra chaining. Okay. So if you get through all the chaining, then you will say, you'll find that it too is proportional to the previous level inputs, AKs, times the gradient that came all the way back. So the gradient delta J here really is how much would the output change for small changes in the input layer. The previous gradient is how much will the output change for small changes in the middle layer. You see what I'm saying? And you'll notice that they're basically, their form is the same. The math may look kind of slightly more intimidating, but if you just go through the chain rule application, the form is the same. It is gradient times the error. Okay. And that would be the update for the weights. If you are into doing this, if you want to doing actually this for at least one example, step by step, I suggest you look at this website. He actually provides a specific two-level neural network, computes the weight updates by hand, and essentially shows how the weights change. It's worth doing it. It's a nice website. It basically worth going through step by step. Okay. So, and so that's one way. The other way, and by the way, so since I'm showing you the videos, there is also, by the way, this thing is big enough that everybody is making notes for this. 3 Blue 1 Brown has a set of nice videos that are useful essentially for mathematically sophisticated, but probably we'll go into a lot more detail than he gets to go in. But you can still watch that if you like that side. It's actually, I mean, I like 3 Blue 1 Brown videos. Okay, what we'll do basically for now is just say that we will compute these gradients sort of numerically in a computational fashion, instead of doing these analytic functions and actually computing the expressions for the gradients, etc., etc. And the way you do it is you essentially have to figure out how to write a procedure that just automatically computes everything. Right? And we'll just get you through steps of that. That's basically what that Andres Karpathy has the nicest write-up that I know of in terms of how to do that. But the textbook has a shorter description, but this one is more useful. I generally feel that people should once know that this can be done so that they don't have to have a shaky foundation. How many of you have written an operating system in your lives? When you can actually, you know that there is a program counter register, which you can change. And when you change it, it starts basically going from there. If you write your operating system once in your life, then there is some sort of a surety that I kind of know how the crazy information technology world is working. You know what is happening when there is time sharing. You know what is happening when you are shifting between processes. Basically, somebody is rewriting the program counter. So now start from here, now start from here, now start from here. So doing it once gives you the additional surety that people who never did an operating system from scratch will have. It's the same thing here. To understanding, backpropagation once, how it is done, will give you a kind of surety that, I'm not just sort of reading a Cliff's Guide, essentially. Okay, so again, as I said, neural net is just a huge composed function. And derivative of a composition of a functions is basically done by chain rule, right? Derivation of composition of the function is done by the chain rule. And so what we are basically going to do is do this automatically in a step-by-step fashion, in a sense. And to do that, we need to understand like two ideas. One is that any function can be written as a computational graph. That shouldn't be too hard. Like as I said, if you have sine x squared, then I can imagine that x is coming into a box, which is called a square box. It takes any input, and it gives out its square. And then that output goes into the sine box. That output is the function, right? Any arbitrary function can be written this way. In particular, neural networks are essentially, irrespective of how complicated they might look, it is essentially like composition of functions, right? I mean, do people first of all see that? So if you have a neural network like this, do you see that these are the inputs? These things are computed in terms of the inputs. And these things are computed in terms of this. That means they are computed in terms of the inputs. So the output is really just a function of inputs, where the middle layers are coming through the compositions. And the compositions are weighted previous layer inputs, weighted sum of previous layer inputs that are thresholded through some G function. Where the G could be your sigmoid function or your whatever, nonlinear function. Right? Okay, so basically a neural network is a big composition of functions. Composition of functions, I keep forgetting to stop that. But anyway, so then the error propagation, essentially, that is that gradient computation in the backward direction can be automated in essence. Okay, and all you wind up needing to do is essentially that even so if once you compute the computational graph, when you set up a network in any of these environments, PyTorch or something, in essence, you're setting up the network. When you set up the network knows how to go forward in it. So computing, because first of all, any network, if I give you a network, you should at least be able to compute. If I give you this network, you should at least be able to compute what the output is for a particular input using a calculator, nothing else. Okay, that much you can do. The other interesting thing is that the other interesting thing that you can do now is that when it is being set up, at every level you can compute a local gradient. At every node you can compute a local gradient, because each node is some small analytical function, like g of the weighted input, g of the inputs. Okay, right? And so you know already upfront when you set up the network what the local gradients are. And what does typically a gradient tell you? Why is it that I get so many more mails when I'm in the class and I forget? Maybe I should just remove this. But anyway, hopefully no more. So the gradients basically tell you, if you make a small change in the input, how much will the output change? Right? For example, x square's gradient is 2x. Right? That basically means that if you give x equal to 3, the output will be 9. The gradient is 2 times 3, 6. What does that tell you? If you were to increase the input 3 by, let's say, 0.01, the x square will increase by 6 times 0.01. You can actually calculate this and see. Approximately, that's what will happen. Because these are Taylor series. Do you guys remember the Taylor series from back then? So the gradient is telling you how as you change the x, how is the function's value changing. So it's kind of gradient gives you the sensitivity of the function with respect to the inputs. Right? Everybody knows their sensitivity with respect to their immediate inputs. What they don't know is sensitivity of the final function with respect to their output, which is what you're trying to minimize. So what you do is you let the back propagation get that gradient all the way up to you. And by chain rule, you multiply these two gradients and then you pass it on to the previous guy. Okay. So in particular, back propagation leverages the fact that gradient computation is basically a local process. At every gate, the gate can always compute its local gradient, but it doesn't yet know how its output affects the final loss function f that's being minimized. During the backward pass, this information comes crawling to the gate. We will basically, that's the thing that's what implementing the backward pass means. We'll show that in a minute. Okay. And when the output gradient comes, you multiply the output gradient by the local gradient and pass it along to the previous case. It's a nice recursive structure. You see what I'm saying? So which is why when you define a network, essentially like a PyTorch or a TensorFlow automatically define the backward pass for you. They generate the code for that. But this is why what they're doing makes sense. Okay, so let's see how that works. Essentially, we'll take some crazier example. This one, 1 by 1 plus e power minus w0 x0 w1 x1 plus w2. This is actually also the example that was written in the write-up. So I'm just walking you through that. And so the computation graph for that looks like this. Okay, notice that really both w's and x's are inputs for this. Right, because I'm also trying to change the w's. Okay, and w's and x's are inputs. In the beginning, there are some initial weights, then I'll give you those values, and then I will try to change what I'm trying to compute really is, this is actually a beautiful point. Let's see if How many of you will get this? Given this computational graph, the gradient will tell you, what we are looking for is gradient to tell us how much a little change in the weight is going to affect the final function. Using that, you will tweak the weights. In doing so, you are assuming that even though x's are also inputs, you're assuming they are not going to be changed. You're assuming those are constants, right? But I have the ability to change my mind. And I say, I'll give you a network. And I say, this network you can't touch. It's already the weights are set inside. I'll give you a picture. The picture currently looks like school bus to you. Currently, the machine is also saying it is a school bus. I want the machine to say that this is an ostrich. What do? I'll essentially take the school bus minus ostrich difference, propagate it to change not the weights, which I can't change, but the pixels, x's. Mind blown? Essentially, that's how adversarial examples are made. That crazy school bus ostrich example that I've shown you, what did they do? They essentially start with the school bus and keep hitting the network saying, say it's an ostrich, say it's an ostrich, say it's an ostrich, say it's an ostrich. And if you do it a million times, it will slowly change the x values. And one of the other things we'll do, by the way, is we'll try to make sure that the changes to the x are not too high. We'll make it not make big changes to the x. So that is what's called a regularization term that we'll talk about later. So make the minimal changes to the input pixels such that this crazy function will just put this guy right over the boundary between the school bus and an ostrich, so that the machine starts thinking it's an ostrich. You can see this? That's what is adversarial examples. When you keep W's constant, change x's, it's adversarial example. If you keep x's constant, change W's, that's learning the network. Okay. Right now, we'll forget about adversarial examples. We'll just do the x's constant and changing W's. So these were the original, weights in the green. And then it's basically going through these functions, multiplications, additions, etc., all the way to the end. And if you were to actually put these weights and these x values into this expression, you will get 0.73. That's the forward pass. Furthermore, when we were doing it, we knew what the values are at every point. Because while you're doing the forward pass, you knew the values at every unit in this computation graph. In the backward pass, what I basically need to do is I'll notice that individual units here, the 1 by x, exponential, -1, etc., they are all essentially analytical functions. I know their gradients analytically. Right? For example, I hope you know this much. E power x, gradient is e power x. Ax, gradient is a. 1 over x, gradient is -1 over x squared. C plus x, gradient is 1. This you know. And so that basically means every one of those units, they know their local gradients, they're weighting. And then the backward passing gradient comes along, they multiply that. With some variations, for example, things like you need to think of what happens for plus and multiplication and max. We'll look at that. Okay, but in general, that's basically what backward propagation is. Okay, so I'll sort of animate this a little. So I basically, I will start when the gradient starts flowing back. It starts at f. If you change 1 unit in f, how much will f change? 1 unit. Okay, so you start with 1.0 as the gradient that's being passed behind. Okay, and that 1.0, and you get to here, you got to 1 by x. 1 by x's gradient is -1 by x squared. But that -1 by x square, that x is the input of this unit. If you look at the input, which is already sitting there waiting for you, that's 1.37. So that is -1 by 1.37 square, which this guy has been holding. That's my local gradient. And when somebody sends the backward passing gradient, they multiply these two gradients and pass it along to the back. Okay. So when you get here, then essentially 0.53 minus 0.53 is essentially now being passed to the next layer. Okay. So now minus 0.53 got passed here, and then I'm adding 1. So this is basically x plus 1. The gradient for x plus 1, I'm sorry, this will be minus 0.5, right? Yeah. The gradient for x plus 1 is 1. That's the local gradient. Okay. So if I then basically take this minus 0.53 and multiply it by 1, I'll get minus 0.53 in the previous level. The thing that's passing in the red is the backward propagated gradient. And everybody takes what the message coming multiplied by the local, pass it back. This is what computer scientists are good at doing. How big can this depth be? I don't care. It's my computer's problem. I'll just set up the recursion, and as long as there is a base case, the recursion will stop. Right? So that's the beauty of backpropagation, in a computational sense. So continuing along, I now get to exponential function. For the exponential function, the gradient is e power x. That is e power whatever is the input, which is -1, e power -1. That e power -1 should be multiplied by minus 0.53. Okay, e power -1 times minus 0.3, that will be minus 2.0, minus 0.20. You see what I'm saying? And then similarly, at this point, it is when I get here, once again, I'm continuing basically multiplying the local gradient by the gradient being propagated, which is basically because of this minus. We are right now, if you have a sense of what is happening, by here we have come up to this exponential of the weights. And then these are the weights minus. So if basically notice what happens, this function, by the time you came to exponential, you must have taken the weighted sum and put a negative, and then passed it through the exponent. So the step before this was essentially putting a negative sign in front of the weighted sum. And minus x, derivative will be -1. So I multiplied -1 times minus 0.20, I will get 0.20. At which point, I will essentially have these pluses because there are other weights being added. Now, this is one place where things get interesting. In the case of plus acts as a distributor. So essentially, when you're doing plus, that means everybody else, there's a single input branch. For operators, there will be multiple input branches. So the question then is, how do you pass the gradient back? For the plus, essentially, it passes the gradient to both directions, unchanged. So it's a distributor. For max, it's a router. Because if some value is max of xy, z equal to max of xy, then a change in x, so let's say this is z equal to max of xy. Let's say at this point x is 7, y is 3. So z is 7. Right? Now if I ask, if I change a small amount in y, how much will z change? It won't change, because right now you're at 7, 3. A small amount to 3 will still be making it smaller than 7. Whereas if you change a small amount to 7, z changes. you understand what I'm saying? So actually the gradient will pass through the guy who is in fact making the max. If there are two inputs and one of them is in fact bigger than the other, then the gradient coming back through max will go to the guy who made the max happen. You see what I'm saying? The rest are slack variables. So max essentially is a router. And then there is one other thing, which is multiplication. That's actually slightly more interesting, but it's still not that hard, actually. So here, so max xy, the derivative will be 1 if x is actually greater. The derivative with respect to 1, with respect to x will be 1 if x is actually greater than y. Otherwise, it's 0. Right? Similarly, derivative with respect to y is 1 if y is actually greater than x. Otherwise, it's 0. Right? Similarly, fx plus y, it's 1 and 1. Because remember again, even though we're thinking in terms of single variable, what we are really doing is multivariable because they are different weights and you're taking partial derivatives. And finally, for fxy equal to xy, the derivative with respect to x will be y. The derivative with respect to y will be x. Which actually means when you get here, this is 2.0 is coming, and this is a multiplication sign. So this 2.0 is multiplied by the y to get the x's gradient, x side gradient. And similarly, this 2.0 is multiplied by x to get the y side gradient. Again, it just follows from elementary differentiation. And furthermore, once you did this, you can sit back and relax and enjoy. Because in fact, that's the beauty of computer scientists learning this as against mathematicians learning this. Because computer scientists, one thing that we get to the table is we have recursion. And we can essentially, the modularity of the programs where you say, recursion basically is built in by the network structure is something that's very easy for you to do. Okay. That's basically it. That's backward propagation. Okay. And furthermore, actually, it turns out that it works well enough that, in fact, if you have a gate, you could actually say the way the computational graph is being written, you can make it smaller, for example. Here, for example, I took this function like 1 by 1 plus e power minus x, and I also unfolded it out. But I could have said that is the sigmoid gate. If I know the sigmoid's gradient, I could just directly use that. So I don't need to pass multiple times. I can just get that number directly. And one of the sanity checks is if you consider this the sigmoid gate, you know the actual derivative for the sigmoid. And the one that you actually passed will be exactly the same thing that you would have gotten if you put x there. That's the sanity check. Okay. Okay. So notice that basically whether you do it this way or the hard way, it's always 0.20 is the gradient being passed that side. Yes, there was a question somewhere. Yes.
What if you had a function like an absolute value function?
Again, absolute value function. Again, actually, max is a function like that, right? So one of the nice things about this is max is really not a continuous function, right? But you can still define the partial derivatives in local neighborhoods. That's the same thing that you do for absolute value. And in fact, that's also what you wind up doing for ReLU function. In fact, it's a good question because, I made a huge deal about the fact that we don't like this, like non-differentiable functions. But one of the functions people use is ReLU. ReLU is non-differentiable. right, at this one point. But then if I know where I am, I know that derivative. One of the funny things that's being done here is I'm never computing the derivative as an entire function. I'm computing the value of the gradient at any given input point. You see what I'm saying? Which is the only thing you need to change the weights that are stuck at that point. Right? I mean, think about this. When you say x square's derivative is 2x, you do realize that x square looks like that. And that depending on the value of the x, the derivative is changing, which is not surprising. So if it is at 4, the derivative, x square's value is 16, and the slope of the line is 8. Whereas at 0, it is 0, because in fact, it's not changing. It's basically in that local neighborhood, the value is just sticking to close to 0. Okay, so the gradient is how fast are the things changing locally. Okay. Other question? Okay. So, yeah. So this brings us to why all of a sudden, yes, go ahead.
Didn't you say that any function can be modeled with 4 layers?
What?
Did you say any function can be modeled with 4 layers?
Yeah.
Isn't that like a ton of layers for a relative?
Okay. Answer him, or I'll give up and stop teaching. Somebody answer. It's a good question. You have to ask yourself local inconsistencies and solve them yourself. I mean, he's asking a very reasonable question. Okay. What is this function doing here? It looks like a big, long function. How do you answer that question? Yeah.
It can be expressed in that many layers, but the size of that layer could be like.
There are actually, the answer to this is there are 2 problems. When people ask, this is the thing, did I ever mention this, that the Anna Karenina beginning, all happy families are alike, every unhappy family is unhappy in its own way. Every question basically is from some misunderstanding. In this particular case, there are at least 2 misunderstandings. One is you are comparing computational graph to the neural network configuration. Notice that this is G, and that itself is this long. We are not talking about the depth of this function when we meant layers. First, get that straight. And second, if you were to actually think in terms of the number of layers, it is true that theoretically any function can be approximated, any continuous function can be approximated with 1 hidden layer, every discontinuous function 2 hidden layers. But that doesn't mean that you can't use more layers. And in fact, one of the interesting questions is, why do more layers seem to help? Nobody knows the answer. I can, say a few things like, if you, for example, one reason is, otherwise it won't be deep learning. What do you want? You want to just do normal learning instead of deep learning? I mean, how are you going to get your job? Right? The bigger point is that it is indeed true. I mean, so basically, there is no clean answer that I can give with full certainty as to why the depth is actually. I mean, so it is clear that if you can represent something in 2 layers, you can also represent the 85 layers. That much you know. One of the interesting questions is, what is this depth seem to be helping? People empirically realize up until now that depth seems to help. Help in what sense? Seems to work. Like, for example, did you ever think about why are like the bridges have certain kinds of nuts? Why not some other kind of nuts? Why should the nuts have the hexagonal shape? Why not some other shape? Well, it works. The bridge didn't fall down. What more do you want? You understand what I'm saying? I'm not saying other types of nuts are not allowed. certain things are important. For example, wheel has to be circular because the ancestors of the people who are not here experimented with non-circular wheels. And they tried to, go very fast on their cart when the, tiger was chasing them. They didn't go anywhere. Some things are important. Others, basically just engineering science. Right now, there is an engineering-wise deep depth seems to help. Theoretically, we don't know why it is helping. And one interesting thing is once you have depth, again, if you have lemons, you can make lemonade. If you have depth, you can say input is now being defined into first level features, second level features, when the first level features, third level features, when the second level features, blah, blah, blah. And in the end, these really deep interior features are being subjected to a linear perceptron. That's a way of understanding depth. But that doesn't tell you why depth is important. Okay. That's a good question. I mean, but for the fact that the computational graph is being confused with the network configuration, which is a different one. Why are people looking for 150 layer networks? I mean, people keep talking about the deeper, the better kind of scenario. It seems to work. That's about it. Okay. Any other questions? Okay. So that basically gets us to the role of GPUs. And the thing is, this both forward pass and the backward pass, you notice essentially there are multiplications, additions, etc. Right? And they just have to be, they can be done in parallel. And so essentially GPUs were originally, for those of you who are old enough, were mostly for screens. Like each pixel in the screen is controlled by a GPU. And so this can be parallelly set. And the gamers really need high-flying GPUs because apparently their life depends on things moving very fast without any shadows, etc., etc. Believe it or not, I mean, while gamers may not have changed the world in good ways in any sense, they did change in the good way in the following sense, which is because of them, these companies like NVIDIA existed to generate, very, basically very powerful, large size GPU clusters, which will be good for doing fast refresh of your, very fast refresh of your gaming consoles. But at some point of time, even the biggest gaming crazy person has bought the cluster that they need, and that's enough. And NVIDIA wasn't going really anywhere. Nobody else was actually competing with NVIDIA, right? And then basically independently, several people noticed that if we are anyway trying to do backpropagation, the two things happen, as I mentioned at some point of time, I should mention it again. The idea of backpropagation was tried and it didn't work and people gave up. What does it mean to say it didn't work? They tried to run it for a few iterations with a couple of examples. It didn't get any useful results. So I said it doesn't seem to mean, that seems to mean that it won't work. But really what they needed was more examples, enter internet and cell phones and everybody taking pictures of their cats, lot more examples. And enter GPUs. And suddenly Jensen Huang saying, whoever said I'm a gaming company, I've always been an AI company. The first time he said this, it was like very hard not to laugh on his face. But now, he's an AI company because everybody wants to buy GPUs because that's the thing that's working. Interestingly, this is not the first time this sort of a thing happened. When I was a grad student, there was a time when essentially all the AI programs were being written in this language called Lisp. How many of you have heard of Lisp? Okay. People have decided that to do AI, you need Lisp. And so what should be an AI company interested in, any company, hardware company interested in AI do? Generate Lisp machines. So they will basically make these machines. I used one of them. These machines, which will be having microcoding support for Lisp. okay, highly complex CISC architectures, not RISC, but CISC architecture. And these Lisp machines in those days, with the kind of chip fabrication we had, they were pretty fast compared to running Lisp on the IBM. And so since everybody in AI is writing programs in Lisp, their programs were running faster on Lisp machines. And so I remember in '85, there was a AAI in Washington, DC, and that time, the president of AAI at that time was Randy Davis. He stood up and said, every company needs Lisp machines. Every company needs 2 Lisp machines per employee to increase the productivity. And then all sorts of things happened. First of all, RISC took off. That means essentially Sun workstations, basically with RISC, you could actually improve the clock speed much faster because the architecture is simpler. And B, people actually weren't doing as much Lisp programming anyway. So Lisp machines bought at $36,000 to $47,000 a piece have become very nice doorstops. It is very much possible that 10 years from now, GPU clusters will be smaller doorstops. Right now, they're useful. You see what I'm saying? Right now, they're very useful. Okay, so that's the role of GPUs, essentially. Then, 2 things I want you to sort of get into your mind when we shift to the next level, which is 1, the fact that if you really understand backpropagation, you understand, for example, that however complex the network is, it's somebody else's job to compute the gradients and change the weights, because I told you the method and the details are just very simple because the program does it. In fact, as Alfred North Whitehead said, civilization advances by extending the number of important operations which we can perform without thinking of them. You used to do differentiation using fx plus h minus fx by h tends to 0. But you no longer do that. But that's important if you get stuck, but otherwise you no longer do that. So the ability to kind of abstract away and say somebody else will do this, and so it's like a box that I can assume will work, is extremely important. Backpropagation allows you to do that. And in fact, we'll see when you get to batch norm, maybe hopefully in a minute, that's a pretty mind-bending idea, and backpropagation will take care of how to normalize the data in the middle of the network, even though that has nothing to do with the final function or the weights. Okay. The second is this. You people know what this is, right? Right. So these are coral reefs. And what is coral reefs? Essentially, a coral reef is a polyp, coral polyp, secreted by the sea organism. Poop over deep time. Okay, gives you coral reefs. You know how coral reefs are generated, but you can't really visualize it as to how slowly these little calcium carbonate pieces will construct themselves into these huge, big, beautiful forms that maybe we co-evolved to appreciate. We can destroy them very easily. That's great. We're extremely good at destroying coral reefs. In fact, I think every once in a while coral reefs get bleached, and I think I've been to Barrier Reef, which is amazing. I mean, I'm not even a good swimmer, and even I'm impressed. Okay, so this is great stuff, but nobody really truly understands how coral reefs are formed. Other than that, I know the beginning conditions, deep time, coral reef. The same with Arizona example, which is Grand Canyon. How is Grand Canyon formed? It's just water drip, drip, drip on bozo rocks. Some rocks are hard, some rocks are soft. The soft rocks will just go away, and the hard rocks will stay closer. So if you ever been to Grand Canyon, the Vishnu schist is the one that's closest to the water. That's a hard rock. That's in the bottom of the organism. That's kind of closer to the Earth's center. The top one is this Coconino sandstone that, a little bit of water, it just disappears. I mean, sort of. So this is much wider. you understand it at certain level, but let's just wait for a Grand Canyon to start happen by just pouring water. That's not going to happen, right? What was changing is the deep time aspect. It's the same thing with evolution. People keep thinking, how can this happen? Remember, it's only 6,000 years back, apparently, that God created the world. So how can it happen in 6,000 years? Obviously, it's not 6,000 years. Obviously, it's deep time. The point about neural networks finding weights when there are, let's say, billions of parameters is they're doing essentially the operations that we just saw previously. Okay, you are very surprised that this looked like a big network. But please understand that, I'm sorry, this looked like a big network to you. This computational graph is just the G function of one unit. If there are 150 layers, each layer with 100 units, then there are going to be 150, 100 functions like this. That would be part of the computational graph, plus all the weights and all that stuff. These are huge, large graphs. They have structure. And you do this, weights will change little at a time. And if you let the weights change often enough with examples, you can see interesting local minima being found. It's not at all obvious that this were going to happen. You understand what I'm saying? It's not at all obvious, because if you waited for some number of iterations and nothing happened, you say, oh, looks like this idea isn't working, I'll look at some other idea, which is exactly what people did with respect to neural networks for a long, long time. You see what I'm saying? And it's easy to say those are bozos. Now I know. It's like a bunch of independent extensions, independent improvements, such as availability of data, availability of data, which had nothing to do with AI. I mean, availability of examples, which has nothing to do with AI because there are cell phones and people take pictures. And availability of GPUs, which has again nothing to do with AI. It was because gamers and the CRTs wound up being used to do this. And that the point of deep time is essentially compute speeds up time, which is why I say that a way of understanding this is how much time would it take for you to train one of these networks, any network that you seem to have heard of, let's say AlphaGo network, on your laptop, which seems to be extremely fast. I mean, when you're editing, the words are appearing, you say Control V, next page comes, all that stuff, you are sending mail very fast. Well, the answer is AlphaGo would have taken 1,700 years to train on a normal laptop. If everybody only had normal laptops, we would have given up on it, saying this is a bozo idea, it won't work. Somebody wound up essentially having Google-sponsored TPUs. It's a complex interplay of development. And I want you to keep that in mind. And then the last thing I want to say before telling you is basically this sets up what you'll have to watch over the weekend, and then we'll come back and talk about it, is there's a bunch of things that engineering tricks, such as the pre-processing tricks we'll talk about, one of which is the inputs. One of the big issues winds up in the original networks. Every G function, every threshold function used to be a sigmoid. Sigmoids have this very annoying property, right? They have non-zero gradient only in a small region. And on both other sides, the gradient becomes close to zero. So you multiply anything coming back by a zero, a fat zero, everybody else basically doesn't get any message. Remember what we are talking about. The gradient from the function is slowly passing through 150 layers, where each layer itself probably is 200 computational graph layers, depending on the number of weights and stuff. You have to pass through all these layers to find the guy at the end, input guy, the weights at the input, how they should change too. When you have deeper networks, essentially the gradient message dies down. So originally people thought the right way to do this is, it's the problem. Again, it's all engineering. You know, if something doesn't work, you don't know the theory. You'll say maybe this doesn't work, some other thing will work. Okay, this triangular wheel isn't working. Square wheel is really the best thing to try. You'll try the square wheel. Okay, so people tried ReLU, for example. Then somebody essentially, sort of parallelly, people have started realizing that if you make sure that your input is normalized to be in this narrow region, then it will be fine. You've been to concerts, right? Poorly managed concerts are good concerts. What is the difference in terms of acoustics? A poorly managed concert, everyone says, right? The really annoying sound. What is that? That is the input saturating the amplifier. If you saturate the amplifier, you essentially get the sound, and then people will leave the concert. A good concert makes sure that the inputs are properly scaled such that no amplifier is saturated. Because one of the problems is one amplifier is saturated, everybody else downstream will be saturated. We know how to keep things in range such that saturation doesn't occur. You could do that for networks. What you'll wind up doing is basically two ideas. One is one simple idea, which is just make the inputs be whatever the inputs you started with, scale them such that they become zero mean and unit variance. I can take data and essentially scale it such that it becomes zero mean and unit variance. Because how do I do it? I'll take the data, take its mean, sigma, compute its variance. Actually mean is mu normally. X minus mu by sigma square. Sigma is the variance. These values will be zero mean unit variance. They will have the shape of the original distribution, but they will be zero mean unit variance. So they won't saturate the threshold functions. This one is called Xavier initialization. People tried that. That was good for the initial level. But in the multi-layers, you start by initializing the first layer, but the activation in the second layer might be already off. Third layer activations might start being closer to the saturation. By the 150th layer, the activation should be maybe such that they'll all got saturated quite badly. Which means when we are coming back, gradient dies there. Which basically means in the worst case, you don't go anywhere because the changes are change W by zero, W by zero, W by zero. How many other times you change W by zero, W doesn't change. That leads to a very powerful idea, which you will hear about in the talk, in the lecture, but I'll also talk about next week if you have questions, called batch now. Where in essence, for every interior node activations, so the activations are computed by a forward pass. After computing the activations, you do a normalization phase for the interior node, which you could do by just doing zero mean unit variance. Except I'll say, no, why would I want zero mean unit variance? Let's say I will have beta mean and gamma variance. Where beta and gamma are just arbitrarily decided. And then I'll throw that into the mix. And now the function being basically computed is in terms of these betas and gammas and W1s to W million. Now you'll say, who is giving me this beta and gamma? The same people who gave you W1 to W million. Your very slow, rich uncle. The same damn gradient back propagation can also compute the right way to initialize the interior level activations. I mean, normalize the interior level activations in a level specific way such that what? Such that the final error is minimized somehow faster. This is batch normalization. this idea wasn't known for quite a long time. So because of which people tried things like ReLU, etc. Once you have batch normalization, you can use any arbitrary threshold function and let batch norm make sure that everything stays in range. And to understand that this is actually possible, you need to know that back propagation will work, and whatever random additional parameters that I throw into the mix that I don't know how to compute, let the gradient decide compute. And then we'll come back next class and talk about the regularization, Bayesian learning, and confidence. But you would have seen this lecture, which already would have talked about it all once. So you will hopefully ask me questions.
Oh, that's good. Yeah. Oh, that was good.
Yeah, sure.
Yeah, I saw that. I thought it was.
I'm surprised.
Yeah, I was.
I think.